Okay, guys, so we've been working with the measurement of segments in a few different ways. We worked on the number line, we worked on the coordinate plane using distance formula, and we even looked at it as Pythagorean theorem. Distance formula and Pythagorean theorem are very closely related. Um, Distance formula on the coordinate plane, and then Pythagorean theorem using that rise and run, kind of turning it into a right triangle. Well, now we're going to look at measurement using measurements of segments and this thing called the segment addition postulate. Totally off the plane. We're just looking at the figures of the pictures. So let's get into it here. The segment addition postulate, um, there's a couple things going on here. So first of all, let's talk about this word postulate. And while we're at it, I'm going to add in the word theorem and corollary. These are just fancy words for rules. We don't have to get crazy with it. Technically, a postulate is a statement, definition, or rule that we accept as fact. It does not need to be proven. A theorem is a concept built on postulates and proven. And then a corollary is also, it's an extension of theorems. But let's just think of them as fancy word for rules. So this is the rule on adding segments. Think about it that way. We've got a really important word here, between. It seems so simple, but for us, between has a very specific meaning. B is between A and C. That means it is somewhere on the segment between them. So it must be collinear. That's really important. It must be collinear. And nothing says that it's in the middle. So we don't want to trick ourselves, right? It does not suggest that it's in the middle. So don't put it there. All right. And again, if we look at an example here, if I went right to the middle, then that means these two pieces are congruent. If B is in the middle, then those two pieces, AB and BC, would have to be congruent. And that's not what we're saying here. So again, really stressing this idea, between does not mean the middle, it means somewhere between. So when you draw this yourself, take that point there and shift it left or right a little bit. If you put it in the middle, you're going to trick yourself into making a lot of mistakes that you can easily avoid. So again, whenever I draw this, I'm going to label my endpoints, and then that other point is somewhere on there, but I'm going to shift it left or right. Now that we understand that, let's look at what this rule actually tells us. And we have a picture of it. B is between A and C. So I draw a picture and I labeled my points. And what we're saying here, is that the first little segment plus the second little segment equals the total. And you can see that written out in the language of geometry. Segment AB plus segment BC equals segment AC. Now again, all 3 points have to be collinear, so the two little segments have to follow the path end to end. You can't change direction. And here we have our segment addition postulate, or the rule for adding two little segments to make a big one. And that should make pretty good sense. Okay. So first of all, we want to understand and be able to draw these things. So looking at number 1, A is between C and T. I'm going to draw a segment. At one end is C, and at the other end is T. A is somewhere on there. But again, it does not mean middle, so I'm not going to put it there. Maybe I'll shift it a little bit to the left. I could have shifted it a little bit to the right. In fact, I can switch C and T. I could put T on the left and C on the right, and A somewhere. All of these represent A between C and T. Okay. Number 2, again, very similar, just to let us see it again. O is between D and G. So I need a segment with D and G on it. And O is somewhere on there. So I drew them both. Now we were also asked to write a segment addition statement. Segment addition statements say this piece plus this piece equals this total. So watch what we do here. I'm going to go back to the first one. The first piece, the second piece, and then the total. Well, the total is really kind of the whole thing. So I'm color coding it so we can see what's going on. The first piece is called CA. The second piece was called AT. And together, they make the segment that goes from C all the way to T. And think about it, if we filled in numbers, if the first little piece was 3 and the other piece was 5, wouldn't it make sense that the total is 8? Right? So you can always test it with numbers to make sure that the concept makes sense. Let's look at the second one. And again, my segment addition statement here, I'm going to take the first piece, which is labeled DO. I'm going to add the second piece, OG, and I'm going to call the total DG. Remember, these are the measurements of segments. Whether you call it DO or OD does not matter. It's the same measurement. So really stressing this idea of what it means to be between, because we have to be able to draw that picture, and this segment addition statement. This little piece plus the piece right next to it. You can't have a gap. This piece, the piece right next to it, equals the total. No gaps, no overlap, no changing direction. So let's just look at a few things worked out. The next few examples all use the same picture. B is between A and C. So you can see the segment addition statement. As long as the picture does not change, the segment addition statement will not change. I would just label my picture. So AB, they said, is 12. BC is 26. And we're being asked to find the whole thing. So that's my X. And you can see that substitution. The first piece was 12. The second piece, BC, is 26. And the third, the whole thing, AC, is X. So we plug it in. And then, of course, we just work it out. X is 38. Well, that was AC, so AC is 38 units. Always, always write your segment addition statement, then substitute. It is really important. Do not try to do work on an equation that was not written. Write your statement, then substitute. And then algebra. So we have a geometry statement that we turn into algebra by substitution. Okay. Now we're going to keep the picture the same. So you're going to notice that the segment addition statement is the same for a few examples. We're just changing the algebra underneath it. So again, looking at our second example, the picture stayed the same, so segment addition stayed the same. This is the geometry. If you get it, awesome. The geometry is not changing for any of these examples. What we're changing is our substitution, so we turn it into algebra. So again, we're turning it into algebra by substitution. I'm going to label the picture. AB is 8. AC, the whole thing, you got to get the label correct, is 21. Find BC, so BC is my x. Well, again, 8 plus x equals 21, so I'm substituting it. And of course, we can do a little bit of algebra, and we find out that BC measures 13. Again, and I told you this, we're not going to change the picture and we're not changing the segment addition. So I'm not even doing anything different geometry. All I'm doing is stepping up the algebra. In this question, AB is 2x plus 3. BC is 4x plus 5. And together, they make AC, which is 56. So I'm substituting for AB, what they gave me, for BC, what they gave me, and for AC, what they gave me. And then I'm solving for x. So I left out the algebra part there, but I'm solving for x. So let's take a look. We have 6x plus 8 equals 56. We're going to subtract 8. 6x equals 48, and x equals 8. Awesome. X equals 8. But that's not what they asked for. Look at what they asked for. They asked for BC, so x equals 8 is correct. We're 90% done, 99% done. And yet, if we don't read the question carefully, we're going to get it wrong. This question asked us to find BC. Well, how am I going to get BC? I'm going to substitute. BC in the question is 4x plus 5. Well, I know x now. So that's 4 times 8 plus 5, 32 plus 5, BC equals 37. So we have to start with geometry, understanding segment addition, substitute to turn it into algebra, and just because we found x doesn't mean we're done. We have to reread the question. What did they actually ask me to find? I'm always going to find x. You're not going to be told find x all the time. Always, always find x. But reread the question. We need to finish it and plug it back in and find BC in this case. They could have asked for AB. They could have asked for everything. So read the question carefully. Reread the question carefully. Again, not changing the picture, not changing the segment addition. So from a geometry's perspective, we understand segment addition. That's the whole lesson. Everything else I'm showing you is algebra underneath the problem. So here, of course, we need to write our segment addition statement, and then we need to substitute. So AB, whoops, sorry about that. AB, they gave us x plus 8. For BC, they gave us 4x plus 2. And for AC, they gave us 9x minus 6. So again, I should be labeling the picture. AB is x plus 8, 4x plus 2, and the entire thing, AC, is 9x minus 6. Labeling your picture is really important in geometry. It lets you visualize what's going on. when I look at that, it makes sense. The two little pieces make up the whole thing. Well, that's it. Add them together. Of course, we found x is 4, and they asked us for AC. They asked us to find AC. So I'm going to take the value of AC. AC equals 9x minus 6, and I'm going to substitute the 4 that we just found. And that's how I'm getting AC equals 30. All right, 36 minus 6 for 30. So I always have to reread the question. Okay, so let's look at a couple problems. Let's tie it all together. Let's take a look at number 1. I'm going to bring number 1 up here on the left. First of all, S is between R and T. That's in the directions. So I need a picture. R, T, S. Now I'm going to label the picture. RS is 15. RT, the whole thing, is 42. And we're asked to find ST. My segment addition, RS plus ST equals RT. So 15 plus X equals 42. Well, subtract 15 from both sides. And X equals, let's see, 37, 27. So this is 27 right here. So ST equals 27. Let's do another. Bring number 2 up here. Again, S is between R and T. So I'm just redrawing it for a new picture. R, T, S. Let's fill in the segment addition statement. The first little piece plus the second little piece equals the whole thing. Now again, I strongly recommend ST is 2x minus, RS is 3x plus 4, ST is 2x minus 1, and RT, the whole thing, is 18. So let's plug that in. 3x plus 4 plus 2x minus 1 equals 18. And we're just going to do some algebra. 5x plus 3 is 18. 5x equals 15, and x equals 3. And now reread the question. It says find RS. So I need to take that answer and plug it back into RS. RS, they told me, was 3x plus 4. Well, 3 times 3 plus 4, and RS equals 13. That is the correct answer. I need to find my x and plug it back in. And while we're here, let's just do, why not? Let's do this last one. So again, I'm just going to scroll up a little bit and give myself some room. Draw it. Directions have not changed. R, T, and S is somewhere. I'm not going to put it in the middle. I don't want to trick myself. That means RS plus ST equals RT. The directions did not change. The picture did not change. The segment addition statement did not change. RT, well, this time they gave me the whole thing first. So RT is 8x minus 2. SR is 3x plus 1. And ST 4x plus 5. So I just want to plug it into the correct place, RS. Well, RS and SR are the same thing. So that's 3x plus 1. ST, and then, of course, RT, 8x minus 2. So I'm just going to bring my work off to the side here, combine like terms. It looks like we have 7x plus 6 equals 8x minus 2. And I get 8 equals x. I reread the question, which says find RT. Well, RT is 8x minus 2. So substitute 8 times 8 minus 2, 64 minus 2. RT equals 62. So nothing has changed across over a half a dozen examples. The geometry has not changed. All we did was change the algebra for each question. And in fact, that's true even in an example like this. AB is 2x, BC is 3, and the entire statement, AC, is 5x squared. Well, again, AB plus BC equals AC. So 2x plus 3 equals 5x squared. The geometry has not changed. What we challenged ourselves in this question with is the algebra. So, of course, we have to remember how to solve this quadratic. We bring everything to one side. So I'm going to subtract 2x and subtract 3. So I set everything equal to 0. It doesn't matter if it's the left side or the right side. We just got to get it equal to 0 so we can factor it. So remember from our algebra review, there is no GCF. So GCF first. Well, there is none. 2, I'm going to do A times C. So that's 5 times negative 3 for negative 15. Third, so I need the factors that add to B. So what multiplies to negative 15 and adds to a negative 2? Well, that's going to be a negative 5 and a 3. I'm going to split B using these terms. So that gives me 5x squared minus 5x plus 3x minus 3. And now I'm going to group and GCF. So I'm going to take the GCF out. I'm going to take the GCF out. And now, since the parentheses are the same, they're technically a GCF. And now, of course, I can set each factor equal to 0 and find out x could be 1 or x could be negative 3/5. So I have my two answers for x. Well, remember in geometry, we can't have a negative measurement. And if I plug negative 3/5 in, it would give me a negative answer for AB. So I test them. I'm going to test both of these in the geometry. And that's an extraneous solution. Meaning it's correct for the algebra, but it does not fit the geometry because AB would be a negative. So I'm left with one answer. X equals 1. And again, I'm going to just plug it back in. AB is 2, BC is 3, and AC is 5. 2 plus 3 really does equal 5, so that's my check. Again, a lot going on in that question, but notice the geometry did not step up. The algebra did. And then we plugged in our algebra and just found out one of the answers didn't work for us. The geometry did not change from the previous questions. And that's really important. All right, so we're going to stop there. And it's a good time to do a little more practice with segment addition.